So welcome to the latest instalment in the series of Methods at Manchester seminars. As you know, these have been running weekly for the last 6 weeks or so, maybe. And they're usually introduced by Angela Dale, who's the director of Methods at Manchester, but Angela's away today, so she asked me to put in for her. So for those of you who don't know me, I'm Ian Lewis, and I'm chairing social statistics here. And I'm very pleased to welcome Nick Shryane from the Institute for Social Change here in the School of Social Sciences in Manchester. And Nick is going to talk about what is structural equation modelling, as it says there, for about 40 minutes or so, and then we'll have 20 minutes for questions, but we will finish promptly at 2 o'clock. So I won't say any more.
Thank you very much. I'm no statistician, so this is going to be like, what's my take on structural equation modelling? So, I'm going to talk a little bit about where structural equation modelling fits into the broader family of statistics. I'm going to talk a little bit about a controversial topic associated with structural equation modelling, that of causality. I'm going to talk a little bit about some applications you can put it to that might be useful. I'm going to skip along a little bit because I've got quite a lot of stuff. I might not finish them. We're going to have some questions at the end. So if you like, if there's something not clear or you want it explained, or basically if you need a clarification, please do feel free to stop me as we go along. But if you just sort of violently disagree and want to have words with me, then you perhaps save that to the end, and we can deal with it then. So it's not really a method. It's, from what I can tell, been cobbled together from several different sort of bits and pieces. It's sort of like an amalgamation of regression analysis, which I can't even think Dalton or Pearson or someone like that who formalised it. Path analysis that was formalised and written down by somebody who was involved in genetics research in the 20s. And confirmatory factor analysis, which sort of bolted on, and that's when people start to really talk about this as structural equation modelling, in the, coming towards the 70s. So it's actually quite an old sort of technique, really. In terms of where it fits, there's always some more general model coming along that contains the model that we're interested in. So if you like, structural equation modelling can do, it's a more general model that includes things like regression analysis, which hopefully you'll be quite familiar with, because that's what I'm going to attach a lot of these relationships to. The idea of path analysis, which is, again, we'll discuss what that is, and factor analysis, again, we'll discuss what those are. But there's other various sort of latent variable methods that include things you can't actually directly measure, like structural equation modelling does, such as latent class analysis and multi-level models that include random effects, that might previously have been sort of different and outside of what structural equation modelling does, but actually, these days, there was a speaker just a couple of days ago in Manchester, Jeroen Vermunt, and others who are working on much more general families of models, general latent variable modelling, which includes things like structural equation models, as well as lots more besides, and sort of unites these things together. So, structural equation modelling had lots of different names. It used to be known as covariant structure modelling and covariant structure analysis, mostly because that sort of gives a hint of what's going on underneath the surface, rather than looking at the expectations and the means and so forth of variables. Structural equation modelling tends to be more concerned with the correlation structure amongst the variables that you're looking at. It's also been termed causal modelling, although that term is becoming less common. And we're going to talk a little bit about causality now, because this is something, as I say, which has got a bit of a history of, I can't think of the word now, when everyone doesn't agree on it, about exactly what the causal status of structural equation models are. So, without getting too metaphysical, and again, this is an area that's alive and well in the philosophy of science, as scientists, we're trying really, and policymakers and things like that, trying to make causal statements about the world. We'd like to say that this causes that, or this is the product of some intervention. That then gives us control over the world, so we can try and say how we might change something. So we're trying to make causal statements, but all we really observe in the world around us is a correlation between two things. Two things tend to co-vary together. So here we've got a nice little box diagram. So we've got two things represented by those little blue boxes at the top, X and Y, and we've got the correlation between them represented by this little curved double-headed arrow. So we observe a correlation between two things, and we really want to say why does that correlation come about. So it could just be pure chance, but if we've got reliable association, then we might start to think about some causal relationship going on. We might say X causes Y. Someone else might say, oh no, Y causes X. They could be reciprocally related to one another with a feedback mechanism. There could be some third, unmeasured cause. These things might not necessarily be causally related to one another at all. It could just be that we've got some unmeasured influence. And so we've tried to make a distinction between things we observe and things we don't in this diagram. The thing we don't observe, that we hypothesize in this case, that it's making the X and Y correlated, I'll put it in a little circle. And so we're starting to build up a fairly standard visual language for path diagrams in structural equation models. Now, whichever of these cases are true, then we're being a little bit, again, probably not detailed enough if we just say, all right, X causes Y. There's going to be a whole causal chain of mechanisms between the supposed cause and effect variables. So, say for instance, we make some causal statement. So here we go. Thanks to the British Dental Association website for the following couple of slides. Hopefully a somewhat uncontroversial comment. Eating sugar causes tooth decay. So we can think about what we know about the world and try and sort of rule out the idea that tooth decay causes eating sugar. And perhaps we use our intuitions about the world for that. But as scientists, we're going to want to know, right, okay, what is the causal sequence? If that's true, then there's going to be some intervening things that enable that to happen. There's going to be some mechanism. So, hypotheses about why eating sugar might cause tooth decay. Well, it's possible they might just make the tooth fairy very unhappy, and therefore the tooth fairy makes your teeth go bad. So that's one idea. Again, apparently this is the preferred explanation by the British Dental Association. They believe that eating carbohydrate-rich foods get broken down into sugars. That feeds bacteria, which produce acids, which rot your teeth, and so on and so forth. Their take on it. So, what we can do at any particular case, just before I move on, is we could say, right, okay, there must be a causal mechanism. I could measure these little causal, these things that go between what we had earlier, eating sugary foods and tooth decay. I could measure these things, or try and measure them, and see if actually they helped me explain this correlation I observed between eating tooth decay. And so, for instance, if I get a good measure of tooth fairies and a good measure of bacteria, I could try and evaluate which one of those is more of a plausible explanation for the link between these two things. So, moving away from causality a little bit, if we think about how we might try and represent this idea of complex causal chains in a statistical model, we'll say, okay, well, how would we get on with a regression model? This is something fairly familiar. I've started to try and point out that this, as well as a nice way of representing sort of causal relationships with the boxes and arrows, has actually got a one-to-one relationship with a statistical model. So we're trying to talk about the idea we've got the statistical model here without the intercept term, just for clarity. We've got a couple of explanatory variables. They have, we're trying to explain the conditional outcome of this y variable here, and that's a result of this x2 multiplied by this b2, this x1 multiplied by that b1, and a little bit of error chucked in there for good measure. So that's a sort of fairly simple regression model. How about if we try and make it, we're trying to include these extra causal variables in the sequence. But when you sort of add things into a regression model, it's very difficult using standard methods to represent this complex causal structure. We can make the model more complicated and comprehensive, but really we're just often just adding in more of the same into the model. So this is where path models come in. So this is one of the parts of structural equation modeling. We've got a model here where we've got two dependent variables in effect. We've got, if we ignore that bit up there, we've got a straightforward simple regression analysis here, where we've got this y variable as an outcome of this z variable. But this z variable here is also an outcome of this x variable up here. So instead of one equation, we've got two now. And so these types of models, and you can imagine you can bolt on extra bits willy-nilly as you wish. Not that that necessarily would be a good idea, but you could if you wanted to. These path models allow us to fit chains of conditional relationships, which you may wish to put a causal interpretation on. So here, this is a mediation hypothesis. We might have observed, say, in the data that there's a relationship, a correlation between x and y, but conditional upon this z variable and the relationship where we say, right, x causes z, and it's z that actually causes y. So it's not tooth fairies, it's perhaps bacteria in your mouth. Then we should observe here, we're saying that there's no arrow between x and y, there's no direct relationship there in this model. So we're hypothesizing that this z completely mediates the relationship between x and y. Good. So, a regression model says, does x predict y? A path model tries to help us answer, why does x predict y? Is it because of the intervening action of some variable z? So we could look at the relationship between, we might buy into this so-called bacteria explanation for teeth and say that brushing actually gets rid of those. So we could have a look at, by including and testing these mediators, they can help us in evaluating these causal hypotheses. So, that's one part of these models, this idea of path models being an extension of regression models, and that's one part of structural equation modelling. The other part of structural equation modelling is this idea of trying to represent unmeasured directly third influences, third variables that we haven't measured directly, but we think are playing some sort of causal part in the model. So as we said earlier, variables can be correlated just due to the action of some unobserved influence. Now often we just we can view these as confounding influences, but sometimes, and in fact a lot of the time in social sciences, we can't actually measure the things that we're interested in. The things we're interested in are hypothetical constructs. And so all we can do is look at observed variables and try and infer something about that. So for instance, a lot of things like, say, social capital, you can't really get a direct measure of social capital. There's lots of indirect things that we think are outcomes of social capital, like being a member of a club, taking interest in civic things and keeping up with local news and so forth. Or ethnic prejudice. Again, you can't really look at someone and you have to wait for them to express an attitude or to move house or to want to or not want to to marry into or out of their own ethnic groups as they define it. So just trying to establish this idea that often we're interested in some, perhaps even in principle, unobservable construct, and we're trying to infer something about it based upon some things we can observe. And factor models are really a way of writing down these assumptions. So we've got the correlation matrix, say, here between some variables. We observe that there's strong correlations among them. We could just leave it there and say, okay, these things are all just correlated with one another in a slightly higgledy-piggledy fashion. Or we could say, well, actually, what if the reason these things are correlated is because there's some unmeasured influence there, F, in this diagram, that is actually resulting in these correlations amongst these variables. So here we've got a very simple, what we could call measurement model. We're trying to measure F based upon what we observe in terms of the intercorrelations of the Y's. So this measurement model would just say, right, each one of those Y variables is just an outcome of the influence of F plus a little bit of error thrown in for good measure. Error and unique variance associated with each Y variable. Sometimes some people have a sort of hard time imagining what an unobserved variable would look like. It's really just the same as another variable, it's just we can't measure it directly, so we have to estimate what we think it looks like. So if we look at some data, this is what we would observe, say. We've got 10 people here, and we've got some scores on these Y1 to Y4 variables. That's what we observe. A factor model would hypothesize a hidden set of data that we can't see, and we have to estimate, that would look something like this. So, for instance, we look at this person number 3, they've got a very, quite a high score on this F. Person number 10, they've got a very low score. So, all these outcome measures we would hypothesize, are the person's F score plus a little bit of error associated with each one. So this person here who's got a very low F score tends to have very low observed variables. They're not all the same because there's little different bits of error that are associated with it. This person here who's got a very high score they tend to have quite high observed variables, again with a little bit of error chucked in. So all this story is, all this on here is that plus that. So we've got this hypothetical model of the fact that there's some unobserved influence plus a bit of error, and that's what produces our observed scores. Just for completeness, in factor models, just like in regression models, you'd have some parameter. In regression, it would just be a B parameter that allows you to reflect the strength of the relationship between these two variables. So if that was an X and that was a Y in regression, that would just be a B. In this factor model, that's this factor, that's this observed indicator, and so we use the Greek letter lambda. That tends to be the standard one that multiplies the effect of the factor on the outcome. And so you'll see that parameter being talked about a lot. It tends to be the one of focus in factor analysis models. That's called the loading. But it's just like a regression of the factor and the observed indicator. So, structural equation models then include a bit like sort of regression model bits, and there's bits of path models in there potentially, and there's bits of factor models in there, and you put all or some of those things together, and that's what we could call a structural equation model. So here we've got two factors and an exogenous observed predictor variable, all in a nice little causal mediation chain. So this is like a latent mediation model, because we've got these latent variables in this mediation sequence. And again, to use a bit of the jargon that tends to get used, we've got the structural part of the model, which is like the relationship among the variables of interest, the constructs that we really think are part of this causal sequence that we're interested in. That's like the regression path analysis bit, referred to as the structural model. And in this particular model, we've got two factor analysis bits, which we would call the measurement model. So we've got this 6 observed variables here, and we're saying that, okay, they actually represent a measurement of these 2 hidden constructs. And that's a hypothesis. We could have hypothesized just one hidden construct and had, like, all 6 of them being part of that. But here we've got 2 measurement models in this overall structural equation model. And so you build up these models by combining measurement bits. Sometimes you won't have any measurement parts, in which case it would just be a pure path analytical model. And you've got your structural part, and that's the full model, structural equation model. So that's what the model is. Often in structural equation modelling, the goal of the analysis is to assess the plausibility of the model as a whole, rather than perhaps in regression analysis, we're more used to perhaps looking at a particular parameter and deciding whether it's significant or not. We still do that, but often the emphasis is on deciding whether this causal model, or this putatively causal model that you propose, is actually a plausible way of describing or trying to understand what might be going on to generate the data. So we're trying to evaluate the model and its plausibility. Now, some aspects of plausibility are really nothing to do with statistics whatsoever, and just to do with what we know about the world and also the research design. So X causes Y. Depending upon what they are, that might just make no sense whatsoever. Does eating turkey cause Christmas? Does having tooth decay force you to eat sugar? Stuff like that. But another big theme in the structural equation literature is the idea of trying to statistically evaluate the fit of the model. And what tends to happen is that you've got an observed set of variables, and therefore they've got an observed set of covariances, and so you've got this covariance matrix associated with the data. And then using various clever Wizzo rules, you can construct what you would expect to see in terms of the relationships amongst the variables, a model-implied covariance matrix. And then you can try and see to what extent your model can account for or look similar to in terms of the way it would predict that these variables are correlated with one another. So there's lots and lots and lots and lots of model fit statistics out there that attempt to do this in various ways. I've listed 2 here for good measure. You won't be short if you look in any structural equation modelling book of some discussion about the merits of these things. And I won't go into them too much, other than just the idea that the goal is always to just decide whether or not the model is statistically plausible or not, whether it can actually try and do a reasonable job of representing or recreating the correlations seen in the data. Now, that doesn't imply, and we'll come on to this later, that your model is necessarily true or even better than lots of potential other models that you could come up with. So again, the purpose of all this model fit and stuff is to try and say something about, well, often the purpose may be to try and say something about a causal hypothesis, about something actually a sequence of things affecting something else. So you tend to use model fit with the idea that if you've got a poor model fit, then there's something not right about the model, and you're not sure perhaps whether it's something to do with the measurement model or the structural part, and there's various ways that you can try and look into that. If you've got good model fit, then what you're saying is the model is a plausible candidate explanation for the data, but so might be lots and lots of other models that you could also have fitted to those data. And so I would say perhaps a not quite represented enough topic in structural equation modelling is this idea of equivalent models. So you'll see in the literature, perhaps someone will write a paper, they'll present a nice complicated looking path diagram, and they'll show some good model fit statistics, and they'll go, ta-da, there we go, solved, on to the next one. But what they perhaps won't do is show you actually, with all those different variables involved, there's probably dozens of ways that they could have fitted the model, perhaps slightly differently. And have they compared it to those models? Have they demonstrated that their preferred way of viewing this thing is actually any better than any other one? And there's a particularly good reference that looks at the case where, rather than just similar models, you can actually have statistically equivalent models in this domain. So you might have, for instance, in this scenario, we've got two models. The model on the left implies that F1 predicts F2. The model on the right predicts that it's the opposite relationship, that F2 predicts F1. Those two models would have exactly and completely identical model fit statistics associated with them. And there would be no way statistically whatsoever to decide between them. So a well-fitting model does not on its own mean that a causal hypothesis is true, just plausible. And you're going to require lots of information about the world and the study design to decide whether or not these things are plausible causal statements. For a review of this sort of argument, and perhaps a slightly different take, there's a nice paper by a chap called Pearl that I think came out in 2000. I'll see if I can add that reference to these slides before I put them up on the website. Okay, so looks like we've got a little bit of time left. Well, quite a lot of time. Rattle through these. They've been very polite sitting there quietly as well. So we've got a little bit of time to talk about some applications that you could use these sort of models to help you with. So, say for instance, we were completely uninterested in making any more causal assumptions about our hypothesis or our model than you would make in a standard regression analysis. You can still use structural equation modelling to try and help you with some of the limitations that, say, a standard regression model would have. So, for instance, one of them, which is often not dealt with at all, is this idea of covariate measurement error. So if you remember our regression model from earlier, we had a y that was an outcome of some x's. And it's fine in terms of the y. We include a little bit of an error parameter, so we know that we're not looking to completely and utterly predict the entire variance associated with y. But there's no error parameters associated with the x variables. In fact, the model assumes that these x variables are measured completely and utterly without error whatsoever. If that's not true, then the observed parameters you're going to see in terms of the effects of the x's and on the y's are going to be biased and weaker than actually is true in the population. And the greater the error, the greater the bias. However, with our factor model side of structural equation modelling, and as long as we've got multiple indicators of the same sort of underlying construct that we're interested in, then we can build a factor model to measure the construct that to some extent excludes these error variances. So here, for instance, we've got a model that, if you imagine this f was just an x, it's just like the model we presented earlier. We've got a y variable on the right, and we've got two predictors, an observed x and this factor. So the observed x, we might assume, say, for some covariates, we might assume reasonably that it's pretty error-free, or it's very low in terms of its error. So something like sets, pretty robustly way of deciding upon that. But we might have a slightly less certain take on some other variables in the analysis. These might represent attitude items from a questionnaire or something. And so if we were to include those in the model, we'd be trying to model the measurement error associated with those in a standard regression model, as well as the variance that we're interested in. So if we think they're all measuring the same thing, we can represent that in terms of a factor, which basically is just the shared variance amongst these items. And the variance that's uniquely associated with each item, including error, is actually tucked away and doesn't influence this structural relationship between the factor and the outcome. And so to a certain extent, we've taken care of some of the measurement error associated with those Z variables. And you can imagine this is quite a neat way of dealing with multicollinearity of your predictors as well. So that, for instance, if you had lots of variables that were highly multicollinear, just very, very related with one another, that's a bad thing for a standard regression analysis. But, again, if you had some sort of plausible hypothesis for why they were multicollinear, and perhaps they represent some sort of hidden construct that you're interested in, you can construct a factor model which takes into account the fact that these things, in fact, requires that these things are all correlated with one another. Missing data, a bane for applied research. However, constructing a factor and estimating it with maximum likelihood estimation, which I won't go into too much, but lots of books out there will talk to you about that, provides a way of combining together outcomes that may or may not, that may have quite significant amounts of missing data associated with them. And as long as you're prepared to make a few assumptions about why these data were missing, you can actually get away with including just about anyone who's got any data whatsoever into your analysis, and not having to sort of chuck away great swathes of people just because they've got missing outcomes on a couple of different responses. So the factor model, in this case, becomes a principled way of combining the information from people, because all it is we're just trying to work out what's the population structure, or at least an estimate of the relationship, the covariances amongst these variables. And so anyone who's got any data to provide about that, is just giving us extra information about this factor. And if they don't happen to have an observation on a particular outcome variable, they're just not providing us with any further information about this outcome. However, and I haven't gone into it too much, but all these sort of models make certain assumptions about when it's plausible to do these things, or when it's reasonable to do these things. But if you can make those assumptions, it's quite a nice way of dealing with missing data. Getting a little bit more complicated now, there's variations on structural equation modelling called multi-group modelling that are quite neat in terms of looking at group differences. So here's one based around a measurement model. Say, for instance, I had 3 items in a questionnaire, and I thought, well, actually, one of these items, I reckon it's going to be a bit sex-biased. I think men might answer it differently to women. They might reflect not the same underlying construct in both, say, men and women. How would I go about trying to test that? Well, what I could do is I could construct a factor model with these 3 items. And I've got a hypothesis that this 3rd item is sex-biased. So what I would do, this would be called a test for differential item functioning in the literature. And this is one way I'd go about doing it. So what I could do is I'd fit a couple of models and compare them. One which assumes that the items are all completely fine and not sex-biased, and one which assumes that there is some sex bias in item 3, and I'd compare the model fit. So first model, I constrain, so I just tell the structural equation modelling program that all the lambdas, all the loadings associated with these items are the same in the 2 groups. So these ones here, I'll select right, they've all got to be the same. Those ones, they've got to be the same. This model just says all these loadings got to be the same. Don't care what they are, but they've just got to be the same in the 2 groups. And we get a model, and we get a model fit. Then I go along and fit a second model, and I say, well, actually, make this model very similar to the previous one, but free this loading here so that it's allowed to be unequal in the 2 groups. And so it can estimate itself to be quite different in the 2 groups if we want to. And then I just compare the model fit of these two models. And if they're significantly different, if model 2, where it's the loading was free, fits the data significantly better than model 1, and allowing these two loadings to differ means that this item has got some relationship with sex, and the strength of relationship between the factor and the item is different in those two groups. So in effect, it means something different to those two groups. So we've used sex here. It could be any groups you care to think of. It could be different time points. So you've got a panel survey. And you say, right, well, this is the answers in panel 1, this is the time point 1, this is the answers at time point 2. Are we measuring, if you like, the same thing across those time points? Have they got the same correlation structure in there? Finally, we've seen it before, a little bit earlier, this idea of a mediation model, a fairly straightforward and simple one here. And you could, right, okay, how could we test, say, for full or partial mediation? We've got some hypothesis that the relationship between x and y is mediated by z. Is that complete mediation? Is there no direct pathway between them? Or is there some residual, direct relationship there? So again, we can get this idea of fitting models that just differ in a little bit, and then comparing how well they fit. So we could fit full model, model 1, and then we could tell the program, right, fit this model again, but constrain this parameter to be 0, and then see how that fits. If there's a significant difference, if the second model fits significantly worse than the first one, using a likelihood ratio test, then we could say, okay, that parameter does in fact seem to be important, and forcing it to be 0 makes the model fit a lot worse. And that's a slightly naive way of dealing with mediation models, but you'll see that a reasonable amount in the literature.
I think another naive question then, how about just having a standard regression model where you have an interaction that affects between x and z? So you have x, and then x z.
That's why that would test the sort of moderation hypothesis, that the sort of differences between these two variables are related to the outcome or the sort of interaction of them. That wouldn't test the idea of a mediation hypothesis, where you're looking for, if you like, conditional independence between x and y, given that the z's there. But there's a useful article, I think it's by Barron and Kenny, in 1986. I don't know if anyone's... But it's quite famous anyway, this chap called Kenny, that's his surname, who writes about the difference between moderator and mediator analyses. So that's a good point. You can fit this type of model using SPSS, and you fit one model and then you fit another model just to do the sort of, you first fit that bit and then you fit that bit, and then there's rules for the way you combine them together, written by this chap called Sobel. But it's quite a fiddly way of doing it, and the more recent research would suggest that they can be quite biased ways of doing it. And again, it's very fiddly when you actually start to do more complicated models. So again, structural equation software, structural equation modelling software is a really handy way of doing these things in a fairly straightforward fashion. So that's just some of the many different things that these types of models can help you do. I'm not going to go too much into, I haven't really gone into much of the technical detail. There are some, some reasonably standard sort of structural equation models make some pretty big assumptions about this, the data. Now, these sort of assumptions are being relaxed by more general, or can be, under certain circumstances, be a little bit more relaxed using more general latent variable software. And you can read about those in some of the references I'll give later. But I'll talk a little bit about some of the more sort of applied limitations and features of these models. And I suppose the first one is that you need quite a big sample to estimate these sort of models. It used to be thought that, again, in the literature, people often want to say, right, a number. Okay, you need at least X number of people to be able to run some of these models. It's not really that, simple. Basically, it would depend if you've got, strong intercorrelations between your variables, strong relationships, and a fairly simple model, then you can go down and perhaps get away with something like a couple of hundred or even 100 sort of people, and you'd be able to fit a fairly decent, or at least working, structural equation model. If you've got a very complicated model with perhaps fairly weak interrelationships between variables, then you're going to need lots and lots more data to be able to get reliable estimates of some of the parameters in those models. So in general, it's a large sample technique. It's really a priori theory driven. It's very laborious to explore, because if you imagine when you've got quite a few variables, there's a very large number of different pathways and things you could relate with to one another. Really, the case is that when you've got a structural equation model, every arrow is a hypothesis. The lack of an arrow between two variables is a hypothesis. You've got really, I would say it's a nice feature of the structural equation modelling. It forces you to think very carefully about your theory and precisely what it predicts and says about what should be related to what and what shouldn't be related to what. Because when it comes to actually writing down the model and running it, you're going to have to do these things. It's quite easy to specify very complicated models in a structural equation modelling framework, but it's much harder to actually work out what they mean and interpret them. So again, this idea you might have really big, interesting theory, but then trying to interpret what the thing means and what some of the parameters mean in terms of that can be quite challenging. And you know, you've got to think again about what's the purpose of my research here. Because it's so flexible and you can do so much with this type of software and these type of models, then it's always tempting to perhaps include a bit more and perhaps test something else. And you have to work out, right, what's the goal of my research here? What questions am I trying to answer? Otherwise, I'll just find out I've spent the last few months just with dozens and dozens of models and I haven't written anything and oh, my head hurts and what do I do? Can I get some help with it? I'll bang on about this one a little bit more. But again, contrary to often as it's put in the applied literature, having a good model fit statistic does not mean that your causal hypothesis is true. Just that it might not be false. You have to really think about, right, I've got my model here, but can I defend the assumptions underlying making causal statements about that model? For instance, if I've got a cross-sectional survey and I've got some data from that survey, and I take some items and I predict some factors and I say, right, this one predicts that one. Why is it that this one predicts that one and not vice versa? Have you considered equivalent models? Again, there might be, for any particular model you fit, dozens of models that are statistically indistinguishable from the model I've actually fitted. Why do I prefer the one I'm claiming is true, or at least the one I prefer? And have I compared my model to models that are slightly different, that would have a slightly different interpretation from a theory point of view, that are statistically distinguishable, to see whether or not my model is better or worse? Even if it's good, it doesn't mean it's better than an alternative that's out there. You may want to think about what software you should use to fit these models. So I'll give a couple of examples here. This is, of course, not exhaustive. There's a piece of software called Amos with a very nice graphical user interface where you can draw your models. And it also works with SPSS and it's available on the campus network. It does quite a lot of stuff, but it's not really as broad and flexible as the second one down the list, which is probably, I would argue, it's got the largest range of things you can do with it, of all the software that I'm aware about at the moment. But it is expensive, so I'm talking about M+ here, which it's got a really large range of models, but you have to type syntax, there's no graphical user interface, and it is expensive. Which brings us on to R, which is handily free, but I don't really use any of these libraries, but I've heard that they can be quite useful. Have a play with it. It's pretty accurate. And there's lots more software besides. If you want to know more, like I say, this was just a very brief tour of some of the concepts associated with structural equation modelling. There's CCSR running a one-day course with me, I think, doing it. That's in March 22nd. If you'd like to find out how to actually get the M+ software to do things, that's what we'll be doing on that course. And there's a fairly decent introductory text that links in the library.